All right, 2734, welcome to the uh, virtual session for Chapter 10 in my absence, and hopefully this works out well for everyone. We will circle back again on Monday to talk about any questions you might have about this video. There'll be times that I encourage you to pause the video and try things on your own. You should, much like in class, maybe work a problem on your iPad and then or in your notes, and then push play and watch my explanation of the problem. So we just finished talking about basic properties of light, and we're going to do a couple. Again, we want to calculate the wavelength. So wavelength is going to be equal to the inverse of the wave number. So our wave number is given is 1710 centimeters minus 1. And when we calculate this, we get 5.848 times 10 to the negative 4 centimeters. And of course, we don't want to calculate our wavelength in centimeters, so we're going to calculate it in nanometers, because typically what we look at visible light in, at least. So our conversion, there are 100 centimeters in 1 meter, and then of course 1 meter is 10 to the 9th nanometers. So this is 5,848 nanometers. And that makes sense because, you know, we're in the infrared region. Visible ends at about 780, so it should be quite a bit higher than that. And this is okay. What if we wanted to calculate the frequency of this wavelength? Well, again, frequency nu is equal to, well, c divided by lambda. So now speed of light, 3 times 10 to the 8th meters per second over our wavelength, 5,848 nanometers times 1 over 10 to the 9th nanometers. Oops. Nanometers in 1 meter. This gives us 5.13 times 10 to the 13th hertz. All right, so that's a relationship between wave number, wavelength, and frequency. Now, here's a point at which I'm going to ask you to do this problem on your own. So pause the video and see if you can come up with the answers here. I'm going to first give you some equations. We want to look at the energy of these waves. So now, how do we relate energy to frequency and wavelength? So our formula is energy equals Planck's constant times frequency. Or we can substitute for frequency, so we can have h over c lambda if we substitute c over lambda like on the previous slide. Or if we have wave number, since wave number and lambda are inverses of each other, we get h times c or times wave number. Okay, and then here Planck's constant is always a constant with a value of 6.626 times 10 to the negative 34 joules times seconds. So that's one to memorize or put on a card somewhere. All right, so try to pause this pause the video and try this calculation here and see if you can do it, and then I will do it for you. So calculate the energy of 1 photon and 1 mole of photons of IR energy, electromagnetic radiation, with a wave number of 1710 centimeters minus 1. All right, so again, we're going to pick the third option above, where energy is equal to Planck's constant times speed of light times wave number, because that is what we have in this problem. So Planck's constant, 6.626 times 10 to the negative 34 joules times seconds. times our speed of light, 3.00 times 10 to the 8th meters per second, times 1710 centimeters minus 1. Okay, and so now we look at this and we see that we have to be in like units. And so we have reciprocal centimeters and meters, so that's not going to work. So let's convert below here the 3.0010 to the 8th meters per second. If there are 100 centimeters per meter, this would be 3.00 times 10 to the 10th centimeters per second. So again, we multiply by Planck's constant, same, 6.626 times 10 to the negative 34 joule seconds times our 1710 centimeters minus 1 for our wave number. And we look at this, and what's going to cancel out? We're going to cancel out centimeters and seconds, and we're going to end up with just joules, which is a unit of energy, which is good here. That's what we want. And so in joules, this equals 3.40 times 10 to the negative 20 joules per photon. So we are measuring the amount of energy for a single photon so far. Okay, so if we want to then do this calculation for a mole of photons, because many times we're looking at many photons at once, not a single photon, we would redo this calculation, start with our input from the previous, 3.40 times 10 to the negative 20 joules per one single photon. Okay. We're going to convert joules to kilojoules because it's going to give us a nice integer-like number. 1 kilojoule is 1,000 joules. And then now we want to get rid of photons, so we have 6.022 times 10 to the 23rd photons in 1 mole of photons. Okay, so now we should have a unit of kilojoules per mole, and this is 20.5 kilojoules per mole. If we think about this in terms of energies of covalent bonds, covalent bonds are hundreds of kilojoules per mole, so a carbon-carbon bond might be 310 kilojoules per mole. So IR is not high enough energy to break a covalent bond, right? We're just looking at vibrational energies and such that we're going to discuss in a little bit. All right, so moving on. How does electromagnetic radiation interact with matter? Right? So the most interesting and chemically rich involve transitions between different energy levels for us. And so there are other techniques like scattering and interference and diffraction that tell you about the bulk properties of materials, but we're not typically very interested in those in this class. Those are covered more in instrumental analysis that you'll get to after this course if you're a chem major. So here we just really focus on those interactions involving transitions between different energy levels. So here we're going to look at all these different interactions that electromagnetic radiation can have with matter. So we can start on the low energy scale over here, and what we see is that these are techniques like NMR, which is nuclear magnetic resonance imaging, and this is similar to an MRI if you've ever had that technique done. All of you have been through organic, so you've probably run an NMR on a sample before, and here we're really looking at changes in nuclear spin. And these are wavelengths on the order of 10 to 10 meters in wavelength. So these are in the radio wave wavelength range and typically low energy. Then we have microwave spectroscopy, which is a change in orientation of electrons or spin. And here, slightly smaller wavelengths, higher energy than NMR, but still low energy. and about 1 centimeter wavelengths. Then we move over to the optical methods that we typically talk about in this class, which are infrared spectroscopy and UV visible, so ultraviolet visible techniques. And so in IR, we're looking at changes of configuration, bending, stretching, vibrational energies, and these are typically 100 micron to 1,000 nanometers in range. Visible goes to about 780, so there's sort of this range between 780 and 1,000 here, which sometimes gets a term of near IR. And also in here, something that's not listed is Raman spectroscopy, which we will not cover in any amount of depth here, but it is a type, or it's very similar to infrared radiation, but here instead of looking at bending and stretching vibrational modes, we're looking at modes which have a change in polarization. So you'll hear more about those in other classes, not here. And then we go to visible interaction of visible light and ultraviolet light, and here we're really looking at the change in electronic distribution across a molecule. And so again, when we're thinking about how electrons are distributed across a molecule instead of across an atom, we have to go to MO theory, or molecular orbital theory. Molecular orbital. And these are, electronic transitions, maybe the most important being like pi to pi star or n to pi star, kinds of excitations. And so a molecule will absorb and excite an electron to a higher energy level and cause an absorption of light. So this is what we were looking at in our iron 110 phenanthrene complex through the Beer's Law lab. And then we go to even higher energy, and we get to things like X-ray. Okay, so X-ray, we can have XPS, which is X-ray photoelectric spectroscopy, and we also have things like X-ray fluorescence, XRF or TXRF. And so here we're high enough energy that we're breaking bonds, we're ionizing, so losing electrons in the case of XPS, or we're looking at inner core electrons in the case of X-ray fluorescence, where we're really promoting tightly held core electrons to elevated energy states. And so this is much higher energy that we're looking at here. All right, so this is a very brief introduction to all the kinds of different interactions that radiation can have with matter. And again, we're going to focus on these optical methods in the center of this slide. Okay, this just shows the electromagnetic spectrum, right? And you've seen this in many classes before, but we're going to be really focusing on this area here that is this area here, which is the UV vis range and IR range. And so we're really looking at a really tiny area of all the energies of electromagnetic radiation. All right, so in spectroscopic measurements, we're going to use some kind of interaction with light to obtain some information about the sample. And so for us, typically we produce something that's in the ground state, so it's the lowest energy state of that analyte. And we're going to apply some kind of stimulus to the analyte to undergo a transition to a higher energy state, or to get to what we call an excited state. Okay, so it can be the absorption of energy that gets us to that excited state, that is our signal. So we're talking about analytical signals, that could be the signal. Or it could be a transition back to the ground state that emits electromagnetic radiation. That could be an emission. So we're going to look at both of these cases on the next slide. So we have absorption and emission here, and in an absorption we're going to look at the incident light coming in, and we have an electron in a molecule or an atom at a ground state, and then we have these excited states up here, and I'm going to just draw it here for emission as well. Okay, so in either case we have an electron that is going to be, in this case, in the ground state. So this is the ground state. And these are excited states. Higher energy states than ground state. And so in absorption mode, a wavelength comes in, so electromagnetic energy comes in and interacts with this electron here to excite the molecule or atom. And so we get an excitation up to a higher energy level, and that higher energy level now exists up here, and we get an attenuation of the light that was incoming, and this change in energy here, change in energy is equal to Planck's constant times a frequency. Okay, and in emission, it's just the opposite. We have an atom that's in an excited state, atom or a molecule in an excited state, and that excited state wants to get back down to a ground state by maybe emitting some energy, and to do that then it can decrease back down to the ground state, and that energy is conserved, so the molecule or the atom then emits photons of light out instead of in, and we're measuring that amount of light out. Okay, so we can then say that that energy or the wavelength or the intensity is then proportional to the concentration of our inner-light present. So now that becomes a signal which we can calibrate and use for an analytical procedure. Okay, so the stimulus can be light. It can be light, so we can just shine light on a molecule and excite it, or light can come out. Okay, it can also be heat, so we can heat up something until it starts to irradiate. It could be particles, high energy particles. It could be a chemical reaction, as in the case of chemiluminescence or bioluminescence. If you think about like fireflies, right, that's a chemical reaction that produces that stimulus. Any of those can work. All right, so we're going to focus on absorption for a second. Okay, and so in absorption, we have light that comes in. Okay, so we have some incident light that comes in. And we're going to give that a symbol of P0, so incident radiation. And then that light is going to come in contact with our sample. So I'm going to draw it as a particle here. Okay. And that sample is going to absorb some light to go to an elevated electronic state or excited state, and out is going to be just some light. So some light makes it through. We're going to call this P sub T for transmitted radiation. Okay, and so some light is absorbed, and then we go on to a detector. Detector here, which then looks at the amount of light that is incident light and the amount of light that is transmitted light, and then can tell how much sample is there based on a calibration. And so here, what's happening in an electronic view is we have some ground state we're going to call E sub 0, and maybe we have some electrons in the ground state here, and then we have some excited states up here which we're going to call E1, and we're going to call E2 for a second excited state. Okay, and these the light comes in and it can promote these electrons in the ground state to one of any number of excited states here for the molecule or atom. And if we have quantized transitions, then we have, so E1, energy of transition 1 would be equal to Planck's constant times frequency of 1, or Planck's constant times speed of light over lambda 1. And the energy for transition 2 would just be the same thing, but a second frequency, or hc divided by lambda 2. So if we think about this in terms of an absorption, how would this look? Okay, so we could have absorbance here on the y-axis, and we have wavelength here, and if we look at the amount of light absorbed, we would get two peaks here, which might look something like this, where this is lambda 2 and this is lambda 1. So lambda 1 is higher in wavelength, which means lower in energy, so that would be equivalent to lambda 1 up here, and this would be lambda 2. Higher energy, lower wavelength. So we get two absorption peaks. High energy over here, lower energy over here. All right, then we have something called photoluminescence spectroscopy, where we're looking at emissions of photons instead of absorptions. So we first absorb photons of higher energy, and then we emit photons of lower energy. We call that red-shifted because if you look at the visible spectra, red is on the lower energy scale. Blue shifted would be shifted towards higher energies. And the most important of these are called fluorescence and phosphorescence. And typically we focus on fluorescence rather than phosphorescence. But how this works is very similar. You have some incident radiation, and same kind of setup here. You have incident radiation that comes in. So again, this is PO. And there's a particle here. Okay, so some kind of analyte. And an analyte absorbs some of that light and then converts it through a process we're going to look at in a second to lower energy light, or longer wavelengths. And so then it emits in all directions. It emits light. Okay, some of this light will not be absorbed, so some will come out and we'll call this PT again. And in many instruments there is a mirror here. And the mirror then reflects that light back at the sample and gives it a second chance to absorb some of that light. And then instead of having a detector where that mirror is, that would look at the amount of transmitted light, which would be the same as the previous slide, now we put our detector at 90 degrees. So here's our detector down here. At 90 degrees. And what that allows us to do is to view the emitted light instead of looking at any transmitted light or the initial incident light. All right, so in an energy diagram, what's happening here is that we have ground state here, and then we have some excited states. So let's say this is E1 and E2. And so a photon of light first goes through an excitation where you have an electron here, incident light comes in, and then we promote this electron up to a higher energy level, say E2, okay, or higher. I'm just showing 2 here, but there could be more. And then this electron is going to want to get back down to the ground state. So it's in an excited state, it wants to get back to its lowest energy state. So it has a couple of options. And what it could do is it could go through a non-radiative transition back down to the first excited state. shown by the squiggly line. And then once it gets there, it gets to this bigger gap and says, okay, maybe I'm now the most efficient way is for me to jump straight back down and emit a photon out. So we get a photon out here, a photon of light released to account for that energy gap there. So this is a very simplified diagram. We're not gonna dwell on this right now. We'll look at a more complex one in a second. So this is a non-radiative, meaning you don't release a photon. So it might just be heat transferred to the solution. And here is radiative. We get a photon out. And so what might this look like? Well, if we have, again, signal on a Y, and in here we're looking at emission intensity. Emission intensity. And here is wavelength. So we would get an initial absorption peak, much like before. So I'll draw that one in red, which would look something like this. Okay. And then we would get an excitation peak there at higher energy. And then we would get an output at a lower energy for the emission we're going to call 1 to 0, which is from the first excited state back to the ground state. And that would be a lower energy photon, so a higher wavelength photon. So it would be redshifted. So again, this is high energy, and this is low energy. All right, so now that we kind of understand how excitation emission works and how just regular absorption spectroscopy works, let's look at how this can be utilized. So again, all species have some kind of characteristic frequencies of electromagnetic radiation that they can absorb. And then this lowers or decreases the intensity of the incident light, which we call attenuation. And so if we think about UV vis, UV absorption, we're going to change the energy of valence electrons with photons, and those changes have to be exactly matched or quantized to the energy state of that molecule or atom. And so if we look at our Beer's law, so this is back to our previous lab, Beer's law says that the absorption of light, A equals ELC, or sometimes you see EBC, where A equals absorbance, and absorbance is in absorbance units, which are sort of odd, but don't worry about anything other than absorbance units. Sometimes you see arbitrary listed. The E, or epsilon, is the molar absorptivity. Molar absorptivity, which has units of m-1 centimeters minus 1. So this is like your slope or your correlation coefficient. Sorry, not correlation coefficient. Your sensitivity of your method, and it tells you, how much absorption you should have per mole per path length of centimeter, 1 centimeter of distance through the solution. Right, and so then that gets us to L or B, which is the path length. So, the longer that the light goes through a sample, the more chance it has to interact with an analyte molecule or atom. So the path length is typically, for most instruments, 1 centimeter. So if you think about a cuvette is 1 centimeter by 1 centimeter. We also have small volume cuvettes that you see. Those are thinner in one dimension, but still 1 centimeter in length, so that the path length is 1. So 1 is standard, but you can certainly buy cells that are different path lengths. And then C, of course, is the concentration. Concentration of analyte, which is going to be in molarity. All right, so if we look at specifically molecular absorption, so now we're going to just focus on molecules absorbing light. We can have three different kinds of quantized transitions. The first one we talk about is electronic, and so this is for UV vis. We're going to promote electrons in lower energy states of a molecule or atomic orbitals for atoms to higher energy orbitals. So we're exciting electrons from maybe a pi to a pi star or an n to a pi star. It's typical for molecules. Okay, then we can have a second type, which is vibrational. Here, this only works for multi-atom species, so it has to be a molecule. And so we have two atoms which are maybe vibrating, and these vibrations between the bond of the two can be quantized. Okay. And then we have what are called rotational as well, which for this rotational motion of molecules. So it's smaller than vibrational modes by an order of magnitude, but it still is a quantized energy transition. All right, so here is our more complicated diagram where we have our electronic states here. So E0 for the ground state, and then we have E1 for the first excited state, and E2 for the second excited state, and we could go to E3, E4, E all the way to infinity here, but we're just showing one. And so if we think about IR methods are lower energy, so these are not enough to promote an electron from the E0 state to the E1 excited state. So these are insufficient energy, provide insufficient energy to cause electronic transitions. So the only thing that we can get are vibrational and rotational energies, which are superimposed on that E0. So all these individual small lines here, you can think of them as vibrational states. We could have a V0, a V1, a V2, V3, and V4 here, say, and then we would also have rotational energies on top of those as well. So it gets very blurred here. But the key thing here is that IR transitions are only going to provide these vibrational, rotational excitations. We're not going to jump to a higher energy level. Okay, and then if we go to something like visible light absorption, this is lower energy than UV, so we're going to put UV over here. This is higher energy, and this is lower. So these are high enough to cause electronic transitions, but UV light will cause bigger transitions, so from E0 to maybe say E2 or E3 or so on. And so here we're going to get these excitations that occur that go from, for visible, we're going to get excitations from the ground state all the way up to E1, but also all the way up to the different vibrational rotational states in E1. And then if we think about UV light, now we can absorb all the way up to a higher excited state and all the way to the vibrational and rotational states of that higher excited state. Higher energy transitions. All right. A couple more definitions here. Transmittance, or T, is the fraction of incident light that is transmitted by the solution. So if we think about our diagram from above, what we're really saying is here, if you remember this, some of the light is P0, the incident light goes through the sample and is attenuated, and some amount here, PT, is transmitted. So here, if we're looking at transmittance, we're looking at the amount of light that's transmitted. Okay, and so this amount of light transmitted is equal to, or percent transmittance is equal to the amount of light transmitted divided by the incident light, so the amount transmitted divided by the total light, times 100% will give us percent transmittance. If we want absorbance, A, which is what you typically see for Beer's law measurements in UV vis, we're taking the amount of incident light that is attenuated by the solution, and it is a log function of the transmittance. So A, absorption, equals negative log of T, or negative log of the transmitted light divided by the incident light. All right, so here is another example for you to calculate. So again, pause the video and see if you can do this, and then follow my example after you've tried it on your own. So example, a sample has a percent transmittance of 37%. What is the absorbance value? So if we're at 37%, if we want to convert it to just transmittance, then 37% is equal to a transmittance of 0.37. Okay. And so if we want absorbance, absorbance is negative log of T, not percent T, but just regular T. So we have negative log of 0.37, and we get 0.43 absorbance units, AU. And so you might ask, like, why do we convert to absorbance at all? Why do we not just stay in transmittance and build calibration plots based on transmittance? And the answer is that putting it in the log scale makes these things linear, so that we get Beer's law, which is a linear relationship, which chemists really like to show linear relationships. All right, so let's talk about some limitations to Beer's law here. All right, so we have two different kinds of limitations to Beer's law. The fundamental limitation is that it's a limiting law, so it's really only valid at very low concentrations of analyte. So when you get to high concentrations of analyte, now you have too many particles in a small amount of space, and these particles don't behave independently. And so the refractive index can change, and we don't get a linear relationship at high concentration. So in order to keep it linear and valid, and keep Beer's law valid, we try to keep our values of absorbance below 1. Some people say below 2, but to be the best, we want to be below 1. So if we're below 1 absorbance unit, what is that in percent transmittance? So here again, we're going to just do the opposite. So we know that absorbance equals negative log of transmittance. So if we undo this, we anti-log, we get transmittance is equal to 10 to the negative absorbance. And so this is 10%. So we really want 10% or less to be attenuated. So if you get a sample that is extremely dark, like think back to the potassium permanganate solution that's dark purple, almost black. If you were to shine a lot of light through that, very little light is getting out the other side. That's why it looks black. So that would not be a good solution for UV vis. You'd have to dilute it a lot so that you get 90% of the light to go through, and that will be in the linear range of Beer's law. Okay, there's also a chemical limitation, and here, what if the analyte you're looking at is involved in some kind of equilibrium reaction that's dynamic and changes with concentration? So the actual concentration might not vary linear when you add concentration of the analyte, because it might change the equilibrium according to Le Chatelier's principle. So you want something that doesn't have a very strong equilibrium arrow in both forward and reverse. You want it to be all the way forward or all the way reverse, so that as you change the concentration, it doesn't shift the equilibrium much. And there are also instrumental limitations to Beer's law. Okay, and so Beer's law assumes that we have monochromatic light, which just means that we get very, very narrow bandwidths of light, so it's like a single wavelength. But for an instrument, it's very hard to provide individual monochromatic light. And so we can have narrow bandwidth of light, but we got to pick a max absorbance value. And so here, if we look at the absorbance over here, we can see that on this absorbance peak here, we get a max right here, at the top of this peak. And if we were to calibrate according to this peak max, we would get this green calibration plot over to the right, which shows a linear relationship. But if we were to pick the side of this peak and not pick the peak max, we would eventually kind of get this limiting function earlier on, which means that we would not be in a linear range for as long. So we always want to pick the point of maximum absorbance when we build our calibrations, as we did in the Beer's Law lab with the iron 110 phenanthroline complex. All right, also we have what's called stray light, stray radiation, so light entering to the detector that does not pass through the sample, and this is not accounted for. So typically we do these things in the dark, and we have some kind of cover over it so that light from the window or a fluorescent bulb doesn't get to the detector, and we count that as light that we are not absorbing. All right, 2 more slides and then we're done. We're going to look at not when molecules absorb light, but when atoms. So we have atomic absorption. Light passes through a gaseous sample of atoms, and only a few sharp frequencies are attenuated. And so if we think about it, instead of being in a molecule where you have all these vibrational and rotational energies that are blurring the E0 and E1 electronic states, now you just have single atoms, so there's no vibrational rotational energies there. And so we get these sharp transitions of light, and these correspond with changes in energy for the electrons within the atom. So instead of molecular orbital theory, pi star kind of transitions, now we have transitions between orbitals in the atom. So these get back to your quantum numbers and your electron configurations of the atom. So if we look at this for a sodium atom, and let me zoom in here for you. So for a sodium atom here, we have that valence electron, which is in the 3s. So we have a noble gas configuration of neon, and then we tack on one extra electron in the 3s orbital, 3s1. And so we can promote that highest energy valence electron to a higher excited state by promoting it to one of these vacant orbitals. And so here you see some of these transitions. We can go from a 3s to a 4p, and we have some energies listed here in terms of wavelengths. We could go from 3s to 3p, and we could then go from 3p to 4s through a double transition, or from 3s to 3p, and then from 3p to 3d, and all these energies are listed here. So for these transitions, only L transitions of L plus 1 are allowed. So here we're only going from maybe L of 0 to 1, which would correspond from an S to a P. So you can see here that we can only go directly from the S to the P's. And then once we're at the P, we could go from L of 1 for P to L of 2 for D. So we could go to a 3D or a 4D. But it's only individual jumps of L equals 1 at a time for our quantum numbers. And so you look here on this energy scale to the right, and what we see is that we have 3s to 4p transition here at lower wavelengths, higher energies, and we have more that are going from 3s to 3p here at higher wavelengths or lower energies. But you see they come out as discrete bands of atomic absorption lines. All right, so let's do one more example, and this is where we're going to stop on this recording. It's long enough already. So the 3s to 5p electronic transition equals 4.363 electron volts, where 1 electron volt is equivalent to 1.60 times 10 to the negative 19 joules. Calculate the wavelength of the transition due to radiative excitation for a 3s to 5p transition. So pause the video and try it yourself if you'd like, and then follow my calculation. All right, so first we're going to think about what equations we want to use. So we have energy is equal to hc over lambda, and we can solve for lambda. So solve for lambda here. Lambda equals hc over energy. And we need to calculate our energy in terms of joules. So we are given energy of 4.362 electron volts, and we're also told that the conversion between electron volts is 1 eV is equal to 1.60 times 10 to the negative 19 joules. And so we get an energy in joules of 6.979 times 10 to the negative 19 joules. Okay, now that we have an energy in joules, we can go back and plug it in. So we have lambda equals Planck's constant, 6.626 times 10 to the negative 34 joules seconds, times our speed of light, 3.00 times 10 to the 8th meters per second, and then all of that divided by our energy, 6.979 times 10 to the negative 19 joules, and we get out 2.85 times 10 to the negative 7. If we look at all our units, joules should cancel out with joules, seconds with seconds, and we should be left with meters. And we're going to convert this to nanometers. So 10 to the 9th nanometers in a meter. This is 285 nanometers. So it's out of scale of this image above for this energy transition wavelengths above. But it would take higher energy, obviously, to go from 3s to 5p. That's a higher energy gap between the two electronic states. All right, so this is the conclusion of the video lecture. Please write down your questions and circle back to me on Monday. Don't forget to do the perusal reading for this chapter and make at least 7 comments on that. Thanks.